thank you very much. Today I will talk about encoding combinatorial optimization problems, but not what is usually done with binary variables, but for problems with integer variables into qubits, because typically you don't have qubits. That would be very nice to do, very easy, but we want to do it with qubits and gates on qubits. And I will only do one application. So this is the max k-cut problem. Yeah, so this work is based on joint work with my PhD student, Ruben, and other people. Just a very quick recap, because by now I assume most people know QAOA and how to encode combinatorial optimization problems into qubits and Hamiltonians. So the setting is that we are given a cost function, in this setting a binary problem, bit strings of 0, 1s, into and this function gives us then the cost. So it's a real number for any bit string. And we want to find the minimum. This can be easy and this can be hard. Many relevant problems admit these multilinear polynomial representations. For instance, if you don't have this last term, then it will be a QAOA, quadratic, but you can have higher order terms. This is very standard setting. And then it's also very straightforward how to write this into a cost Hamiltonian. So just take all your bit strings, order them, and then in the diagonal, you just put in the cost. And this can be formally written by this, which is basically just this diagonal. And there's a very well-known mapping how to do this, how to go from a cost function to a Hamiltonian. It's given by just this transformation here. And the order, if you have a quadratic problem, then you will also get a quadratic Hamiltonian, or quadratic terms in your Hamiltonian. And that means like two interacting only by neighbors. If you have a higher order, then it will also be higher order. The terms between this not omega, W and alpha, they change slightly, but the order doesn't change. And then what you do is you make the ansatz. You have a phase and a separating Hamiltonian. The phase one encodes your problem. So it's a rotation defined by the problem Hamiltonian. And so it just applies phases. And then the mixer has to do something non-trivial. So it should not commute with your problem Hamiltonian. And it actually, changes relative phases, relative probability amplitudes. And then you're given some initial state, which should in some sense be efficiently preparable. They're very different. The standard ansatz is you have one parameter per layer, but then you can have the free ansatz, which can have any number of variables, or you can look into the symmetry of the problem and tie some parameters together. So you're given this objective function then, and then your classical optimization just changes this variables. So the thing that we want to talk about today is how can you do this for when you don't have an integer. So the problem is the max k-cut problem. There you are given a graph consisting of vertices and edges. And what you want to do is for each vertex, you want to assign, now it's called a color. So you have colors from 1 up to k. So you have k colors. And you want to do it in such a way that if you go through all the edges, and if an edge has two not the same colors, then this qualifies as a cut. And then the weight of this edge is accounted into the cost function. And you want to maximize this cut. So just on a very high level, there are, of course, different encodings, and this is fairly straightforward. Also, classically, you can do this. So one way is to the one-hot encoding, which means each vertex has to have more than one qubit or one bit. And one way to do it is just to have use k bits for each vertex, and then you have this one-hot encoding, which indicates on the kth position, you have a 1, the rest is 0. This, of course, not very qubit efficient, and actually the feasible subset is becomes exponentially small with respect to k, because you only use k out of 2 to the power of k feasible states. So it's bad in two terms. It's very inefficient. You can do exponentially better with respect to k, and the feasible subspace becomes exponentially small. So it's of course much better to do a binary encoding. So you encode your colors k into a bit string, and this gives you of course logarithmically many qubits that you have to use. If it happens to be that k is a power of 2, then it's very straightforward. There's no ambiguity, so to speak. So you can use the full Hilbert space. You can just use the standard X mixer. And also the binary encoding is very straightforward. If it's not a power of 2, then it becomes much more interesting. So there are two ways. One way is to use the standard X mixer, but then have some equivalence relationship between, because you have k different colors, but you have some colors need to be put in the same equivalence class. So let's have a max 3 cut, for instance. Then you have 0, 1, 2, or 1, 2, 3, 4. So you can, for instance, specify that 3 and 4 means the color 3. This is what one way to do it is. The other way is that you use only the subspace that has k colors. And these two different ways of encodings can be enforced. The second one, where you use a subspace, you also need to have a mixer that never goes into this other subspace, which has the advantage that your problem Hamiltonian is much easier to encode. But you pay with a more a harder mixer, and your initial state needs to restrict to this subspace. So this is the formal way to write it down. So you use log 2k qubits per vertex, and then you need to have the Hamiltonian, which is basically a projection onto this subspace with some equivalence class. So this specifies which colors mean the same thing. And then we looked into how you do this in a more general setting. So this is just written down one more time, that you have this, you're given a subspace B, which is a span of certain computational basis states. You have the projection operator onto this, and then what you want to do is do the real-time unitary evolution of this operator, which means it does nothing on the orthogonal space of B, and on the space B, it applies a phase. And of course, you can then apply some permutation operator, which shifts them into the first, in this case, order of B, or the first B sub computational basis states. And then we looked into how can you do this more generally, and you can have this subspace controlled Pauli operators, which this is in general. You can have any Pauli string sigma and a projection operator, and if they commute, then you can implement this, and we proved this with a depth n times b, and that is the C naught size n times b. And if you are fault tolerant, you need to approximate your rotational gates, and this scales like this, where epsilon is a given tolerance. Before we go into the theorem, a quick definition. I think the best is to just look at an example. We call this the Pauli X-generated, X-orbit generated subspaces, which has a very specific structure. So let's say it's given by the generated group of x1, x3, and x2, x3, x4, applied to some state. Then, of course, the group is given by just the identity. Group has to have an identity, the element itself, and since it's only two operators, also the product. And if you apply it to 0, then the subspace generated by this is given by these four states. And in general, this always works, that you can define this, or if you have given this, then it admits a even more efficient implementation. So the theorem is the following. We have this Hamiltonian, which we want to implement the unitary evolution of, where the Pauli string and the projection operator have to commute. And we can realize the evolution then by these aforementioned scalings. And if it's Pauli X generated, it's even more efficient, because then it's not n times b, but n log b. And also the number of T gates is much more favorable. It's also only dependent on n and not on b. And the depth scales as b log n. So that doesn't change. So the overall structure, it actually depends a bit on which Pauli string you have. If it's the identity, then it's just you reorder your bases and you apply this subspace controlled phase. If it's only a set Pauli string, then it's still a phase, but you need to apply it for the plus and the minus subspace. If the x is non-trivial, so there's an x part of the Pauli string, and it does not commute with a set part, then it's a y rotation, otherwise it's an x rotation, controlled x rotation. And the proof is very instructive. So we only do it for the easiest case. The rest is basically a bit more technical, but the same thing. So if the Pauli string is identity, then you can always, of course, map your or your states in B to the first B computational basis states. That's just a straightforward thing to do with this transposition gates. And then, of course, if you apply M projection M dagger, then it maps J to Zj, and otherwise it's 0. Sorry, that was too fast. So therefore, we can write this, then it's just, of course, the first J strings, and we can use this in order to write it as in this form, where we have this subspace controlled, or we call it low pass controlled phase gate. So I need to define what this is. So these are, it says frame title, interesting. So this is the example. So if you want to apply the unitary on the target, unitary U on the target qubit, depending on if you're in the first one computational basis states, then you just apply a zero controlled unitary. If it's the first two, then actually it doesn't depend on this part. Because if you count in binary, then you basically you go through the first. So let's say for 5, you count 0, 0, 0, 0, 0, 1. So the first part will always go through all the bit strings. So and that you can see here that, for instance, here for less than 4. It does not depend on these two, depending on if it's big or little endian encoding. Then this you have counted through all the bit strings, so it does not have a control here. And this, in general, admits the part, so it's always order n n controlled, multi-controlled unitaries. So this is maybe straightforward, but it's part of the result. One way, so I have a couple of examples where this is relevant. One way is for the qubit excitation operators, which show up in electronic structure problems, Jordan-Wagner transform. And these act non-trivially only in 2 computational basis states. So they maps 0, 0, 1, 1 to the opposite 1, 1, 0, 0, 0. So if you know about, you can write it in this form here, which is basically ensures that the parity of the first n bit strings has to be the same, and the last one has to be the same, and then you have this middle part which says it has to have odd parity. That's why you get only 2 states, because you yeah, and you apply this rotational Y gates between those two. That's the general form, and we can utilize this. Maybe I can go to this already. So the standard way to do it for this excitation operators with 4 terms. So yeah, is to write it in the Pauli basis, and then you have 32 of them, and you need to do the basis change, and then the this controlled C0 gates, rotation, and back and forth. This is, of course, not the best way to do it. It's a better way to use our theorem, and this is also known from before, but it follows also from our theorem, so it's good to know that it coincides with the known results by this construction here, which is only 1 term. You pay with a multi-controlled rotation gate, but it still will scale much better than the other term, which has 2, in general, exponentially many terms. We also can apply to the transposition gates themselves, where you basically swap X with Y and exactly, and do nothing on the other states. And the best known, there's a, I think it's PRX result from 1 or 2 years ago, which is the almost optimal implementation. It's even the title, where they have this construction here. So they use an ancilla gate and all these, and these multi-controlled, so these Toffoli gates. We don't need any ancilla gates, and we only need 1 of these multi-controlled unitaries, multi-controlled X gates. So we are much, much more efficient. And unless someone points out that this is known, then we actually beat the almost optimal by, we don't prove it's optimal, but it's almost obvious. I don't know how you would improve it even further. You can also do it with for lattice gauge theory. I'm not going to go into details, and you can apply to constrained mixers. This I'm not going to cover in this talk. So you can apply to the encoding of the phase Hamiltonian of our max k-cut. If it's a power of 2, it has this easy and known construction. And you can apply it, I just flashed some results here. You can apply it to the max 3 cut, where you can apply the phase encoding like this. Or then for the 5 cut, for instance, you can have a balance encoding, where the size of the equivalence classes has to be as balanced as possible. So you don't want to have one which is large and a few others which are small. Then the balanced ones looks like this. And the less than 5, where you have the first only 1, and then the last chunk is all the rest. It's slightly better, but as we will see, it doesn't perform as well. So you can the 5 cuts can be implemented in different ways. And then I just jump over this. We can do it all. So overall, we have these 2 encoding if it's not a power of 2. The one is to use the full space and just have the equivalence classes. The other one is to restrict to just K states for each vertex. And they scale, of course, differently. If you use the full space, you don't, you have it easier with the mixer and initial state, but you pay with the phase Hamiltonian. You can see this here. It doesn't depend on the vertices, but here it depends on the vertices. So yeah, it's a balance between the 2. What is maybe more interesting is to look at some results. So we took the largest we could still run, because for the max 8 cut, for instance, you need 3 qubits per vertex. And these have 2, 4, 6, 8, 10. So we needed 30 qubits to run this. And we couldn't do it with 1 more qubit. It took too long. For these 2 graphs, so one of them was unweighted, and the other one was weighted. Parabase was weighted. We got this 2 different results. The optimal is, of course, to have the approximation ratio to go to 1. And the best known classical is always this Freer's theorem, which in this case, for this small instance, will probably give you exact results. But this is just to indicate what is the guaranteed approximation ratio. And you can see that you can do different kind of mixes, and the one that actually is overall, I would say, the best is this Grover mixer. For instance, this one Grover mixer, which is a Grover only on the vertices. The global Grover mixer actually is the worst, but if you do only mix the colors in each vertex, then this is actually the best mixer to do. Yeah, I think that's roughly it. So if there are any questions, I can try to answer them. If not, then thank you very much.
Franz, just a question.
Yes.
You didn't put a reference to your paper. Is this from your paper from 24?
Yes. This is a mixture of two different papers. One is the max k-cut encodings of the max k-cut, which also is depending on another result from this compact construction of these unitary evolutions of the sigma times projection. It's two different results.
From 21, and yeah, I was just interested in this, but
yes,
I need to read up a bit.
Yeah, I can send the references later if it's interesting.
No,
Thank you very much.
Yeah, thanks.
Yeah.